In this module, we're going to look at topography, kind of the lay of the land, the surface features that are on it, the changes in elevation. This is a site near Alfred that I've selected for us, and we're going to take the building that we made in the last module, just duplicate it, and then place it on the site so we can deal with all the issues that happen when we have changes in elevation. So we'll be making, um, a platform or a quad for it to sit on. Um, we'll deal with some exterior features like retaining walls. This is an older drawing, but we'll add a parking lot to the back and we'll define some of the surface features like the roads and some of the vegetation on it. But I'm going to provide all of the geological information, the topography for you. I'm going to import it and I'll describe a little bit how I did that. But we're also going to do this week as an in-class assignment associated with lecture. We're going to look at building our own topography, actually just laying down these what are called isobars. I'll describe that in a minute. Um, and generating our own changes in surface elevation. And so we're going to get a bit of a compare and contrast about two ways to generate this idea of the shape of the land that we're working on. And the reason for that is sometimes we're working with existing conditions, and sometimes we actually want to modify the topography of the land. So this is an example of a building where the architects actually started with a site that was relatively flat and decided that they could add a nice feature of an outdoor activity that was carved into the earth. So it's almost like this is the first floor, this is the basement level now carved out for some exterior space, but with the advantage of being below grade and the isolation from road noise and the privacy that's developed, the visual privacy that's developed by just going down one level into the grade. So in this case, the architects needed to modify the site models, existing site, to features that weren't going to exist until it was constructed. So a little more on this idea of topography, um, shapes and features on the surface of the Earth. Mostly when we think about topography, we'll think about those changes in the levels. That'll be the most important and critical thing. But there are obviously other features, existing buildings, um, landscape features like lakes and ponds, water, uh, watersheds, wetlands areas, all kinds of things that are denoted many times in topographical survey data. And so here we have what would be a typical geological survey map that you might use for hiking. And it just shows just some of the basic features of what these kind of maps have. Uh, we look at these maps have been developed because they are two-dimensional representations of three-dimensional spaces. And isobars, this idea of these lines to categorize areas of equal height, is critical to the understanding of these. So we're used to working in 3D model space, and we're not really concerning ourselves many times with this idea of showing elevation in two-dimensional plan. But historically, obviously, without computers, maps needed a way to convey this idea of changes in elevation. So the concept was established of this idea of isolines, lines of equal elevation, and they're incremental, like 10, 20 feet, 30 feet. They can be any actual dimension or increment that you want. There's some established standards for that for different kinds of maps. But the idea here, and this I think describes it very well, is this is a show of how the contours of a hill change with those changes in elevation. And once you become accustomed to looking at maps this way, it'll be very easy for you to then look at a map like this and understand this to be a peak, high point, um, down and seeing all of these isobars continuing down to where we're at 700 feet here, we're up at 1100 feet here, and we're going down to what would be a ravine or creek bed. You can also see where these isobars are very close together. That's a point where the slope is very steep, kind of like a cliff or a ravine around that river. And in our case, we're going to look at, we have a lot of wonderful hills and changes in topography in the Alfred area, so it seemed like a reasonable place to work our site. And we also have, and I want to take a minute now to kind of bring up the point that we do have a very unusual site, our campus, because of the changes in elevations in very short areas. In many places, campuses are sitting on relatively flat land, but this campus is carved into, from one side of the campus to the other side, there's a change in elevation of probably 2 stories. So just walking around campus, you'll get a great feeling for how architects and designers have had to deal with buildings and changes in elevation. And we know that very well. We'll enter at a third level in the SET building, and we can exit at the second floor level in another part of the building. So, and we're both coming out at grade level. So here's another map. I thought this is really beautiful maps that Google Earth generates of topography. These read very well. I'm including this one so that you might think about using this in presentations or this style of map for presentations. You'll notice now how we have both the isobars, but we're really getting the added advantage of casting some shadow detail in this, as if there was an imaginary light coming from above to help define these changes in elevation. And that idea of isobars is really, as I've said, important for describing geometry on a flat plane, like a map or a printout. But in computers, we do have the advantage of actually being able to physically represent that in model space. And the way we do that is we no longer use the idea of isobars, but we actually use a mesh surface that we can warp into 3D space. So here's an example of a polygon space with the triangles pulled into three-dimensional shape, and another example of it, and I believe this is right out of SketchUp. Here we have a, a three-dimensional a three-dimensional map made of polygons. You'll notice that there are more polygons where there are rapid changes in elevation. They're smaller, but they're also a denser level. And where there's subtle changes in elevation, the polygons are larger, so there's fewer of them. But you can see how this is a very effective way of creating a mapping of a three-dimensional surface. And so that's the technique that I use to import the topography that we're going to use. I used the software SketchUp, which is a relatively common piece of three-dimensional design software if you haven't used it already. And it has a unique feature of allowing you to import this three-dimensional geometry. In previous sections of this course, I've asked the students to do this, but it's a really long and tedious process, and it requires the availability of software. So the last few years, what I've done is I've actually gone ahead and done this process for you, and I want to show you how you can actually learn it yourself if you need to. But in the course of this module, you won't need to because I've already accomplished the task. So what I did is I found the site that we're going to work on. I imported that into SketchUp, and then SketchUp allows you to extract the 3D geometry and the map of the bitmap of the surface features together, and I make it easy for you to then combine them into our BIM modeler. And that's well described in the project module. So I've also, though, hyperlinked so that you can learn this on your own in the future if you need to for studio work. This is a tutorial that is really nicely done that shows you that whole process. And at any time you need to really grab this information again for yourself, there are multiple YouTube videos that describe this technique of gathering 3D site topo surfaces from SketchUp and getting them into Revit. Now, I'm describing this technique, but in fact, there may be new incarnations of Revit and BIM modelers that will eventually eliminate this need to use an intermediary to get your data in. There really is no reason why Revit couldn't have a plugin that allows that feature. And as of this recording, I don't know of any, but that could happen any day. We're always going to be required to bring to our studio projects, our sites, as much information as we can. So I wanted to make you aware of other resources for data. One is the U.S. Geological Survey. They have rich maps that are available for you for both the topographical features of the lay of the land and also the features of things like buildings and other elements. And so this is one of the go-to sources, but it's not your only. What's really come on strong in the last decade or so is the idea of geographical information systems, the idea of organizing nationwide, actually globally, data about where buildings are, where how land masses are in three-dimensional space. Um, Almost too many features have been recorded into what's called the ArcGIS system. Um, Locations of utilities, roads, if it's a built feature or a natural feature, many times it's been recorded into this very accurate graphical map system that has many different ways to access. And I think this is probably hyperlinked and it will take you into all kinds of information about GIS. Um, One of the things I forgot to mention was this idea of identifying parcels, the land where the ownership of land starts and ends. Um, so there's a rich amount of information available to you, um, and it's kind of out of the scope of what this part of our project is. But I can't I can't touch on topography without introducing these other kinds of reference materials. And so this is another hyperlinked a source, ArcGIS Urban, and this will take you out to um, city level or urban environment mapping systems. Some of these resources have free trials to them, so you can import rich information. It would be, for example, not uncommon to be defining a project maybe in Manhattan or something, where you might want to import three-dimensional data of building locations and for preparation for a park or building development. And this might be a resource for you. And it's also, as you can see here, it it's not just the physicalities of buildings. It can also be number of people who are occupying it, travel routes, all kinds of information that would be useful for determining the value or the context of the site that you're developing on. And obviously, this idea of, I've discussed it, establishing the idea of a digital twin, of some kind of a digital asset that is an accurate representation of what exists in reality. So once again, just another resource that I wanted you to be aware of that kind of fits into our subject of topography. Um, One of the things that I'm going to teach in the very end of this course is a way to use a node-based parametric modeler. It's called Dynamo. It plugs right into Revit, and this is the start of a way of bringing in this kind of geology, typographical data, building location information into our Revit environment, our BIM modeling environment. And because I'm introducing it at the end of this course, we're not actually doing anything with this, but I want to make you aware of it because it's very useful to you. It could be very useful in the future. And I think this is actually one of these is hyperlinked. So this will take you to OpenStreetMaps, which allows you, and I'll just click through this quickly, to select the location and then get into open up Revit and then import data. And you have to use the software that we are yet to learn, that is Dynamo, to be able to bring in this building information and populate maps. So here we're going through the idea, that's the geometry of buildings being imported, changing them into three-dimensional information and eventual building sets like this, and happening right inside of Revit. So then we have our site context for a project we might be working on. So once again, just an introduction to this. This is all going to be information that you may want to make reference to a year from now. So I want you to just keep in mind. You can come back to a link if you click through to this, or save that so you'll have for future reference to it. Once again, Dynamaps and Revit. Um, and then I guess just a few last things on topography at the architectural level. This is actually this is a project for a friend of mine that I'd recently done. He asked me to import a CAD model in and then get it into a format that he could use. He works in Vectorworks, which is another BIM modeler. But I thought it was just useful. This is a survey that he would have paid a survey company to do. And you'll notice that it has these rings here and center points. These are the trunks of trees, saying it's a 37 inch deciduous tree, 37-inch probably diameter or caliper tree. Locates it on the site, shows you where the canopy is, um, and can help you make determinations about where you may want to put a building, whether you want to destroy or remove trees, and hopefully, I guess the better way to say it is preserve trees that might be on the site. And all kinds of other features can be recorded by a surveyor. So, for instance, stone fences and other features, garages, existing buildings. So, a survey topographical map provided to you can be a really rich resource for all kinds of things that you'll be doing in design work, and save you just a ton of time if you can find a relationship with your survey company and ask for the right kind of information right away. And we'll try to touch on this idea of topography if next semester I'm teaching environmental controls. We'll look at just doing some minor modifications to the surface of the land to create things like retention ponds. Once again, not relying on just the existing lay of the land, but actually modifying it to create specific goals. In this case, in our project, we'll look at creating a retention pond that allows for drainage off of paved surfaces. So just a brief introduction to get you started. I hope it helps to contextualize and make the two modules, the in-class one and the lab one, more meaningful for you.